So I just finished the slide. This part, the first part was what we discussed last week when I showed you the Python simulation for concurrency. Okay, so basically sequential execution, E2 needs to wait for E1, E3 needs to wait for E2, and so on. In a concurrent execution, E4 only needs to wait for E2, right? But in a concurrent setting, you can actually only run each of these one at a time, right? It's just that from a logical point of view, you can actually swap these two. Okay, because E4 only depends on E2, so if you run E3 first, it's fine. In a true parallel setting, this 3, which does not have any dependencies except E1, can actually run at the same time. Okay, that's a true parallelism. And in fact, for most modern processors, there's really not much difference between concurrent execution and parallel execution. Alright, but E7 have to wait for E3, E4, and E6 to finish before you can execute. This is what we call as a thread. Within a single thread, the execution must be within that particular order. Okay, it cannot be rearranged. But among different threads, you can have different interleaving. Okay, so we have this kind of hierarchy where the operating system controls everything. And the operating system, when you run a single program, that will constitute a single process. Okay? So the operating system will kind of try to run each of the processes concurrently. So if I have this and this one running, these are two different processes. One is Adobe Acrobat, the other one is a web browser. The web browser doesn't have to stop when I'm having the Adobe Acrobat in front, right? So that's what it means to have a concurrent execution. Now, but process is very heavyweight. It has to take care of all the possible controls. So people created a lighter weight element that can run concurrently, and that's what we call as a thread. So processes can have multiple threads. And in fact, most of the library can actually, like the C POSIX library, can actually let you control each of the individual threads directly. What we want to discuss today is something that is actually lighter than threads. It's in the context of Go language, they created this thing called Go routines. Go routine is a very lightweight thread. And because it is very, very lightweight, the advantage is that you can always create Go routine and dismantle them easily. Okay? Creating a thread still is much more heavyweight than a Go routine. So you have this hierarchy where this one can have multiple threads and each thread can have multiple Go routines. And then we managed to simulate concurrency. Here I didn't use yield, I used the step function using a higher order function. You can have multiple threads running at the same time, and then we create a scheduler. In the context of operating system, the operating system has its own scheduler. So every process can be scheduled to run or not. There are many different ways to implement the scheduler. You can have a batch. One batch means that as soon as it comes, you run until completion, or you can have round robin. So you can basically rotate each of the processes that they each run for a particular amount of time before being switched out. Okay, but that's for operating system. Okay, so then we created a randomized scheduler that allows us to have interleaving, and then we create this communication channel using first the shared memory, and then using the shared memory we can actually create communication channel, which abstract the shared memory into two functions. One is to send and the other one is to receive. there are multiple ways you can implement this, and typically you can classify them as a blocking or non-blocking. A blocking send will wait until the message is either in the pipe or it is received by someone. A non-blocking send will basically just send and then just immediately return. A blocking receive will wait until the message is received. Okay, so we have a different kind of sending and receiving. And for Go language, it is actually a non-blocking send and a blocking receive. So whenever you call a receive action, you need to wait until there is an actual message. And this can be used to actually synchronizes between multiple Go routines, which I will show you later. Okay? So we create a communication channel with two functions, send and receive. This is one rudimentary implementation of it. Okay. So let's look at the Go routines itself. And before we talk about Go routines, let's talk a little bit about the Go language. Okay, this is how the Go language is created. You can give a package name, you can have an import, and then you have the main function. Okay. When you run a particular Go program, the main function will be the one that is going to be executed. Okay, so you can have things like, this is already imported. FMT contains the print line. You can run this, you can get the output, hello world. Okay? Semicolon is again optional. Now, let's look at the Go routine itself. You have functions. If you call the functions without the Go, it will be run until completion before you continue the next one. When you give the Go keyword, what it will do is that it will put this inside the Go routines, package it as a Go routine, and then it will try to run it if it can. The function will return immediately, so you can create two separate Go routines at the same time. This. If you try to run this, unfortunately, it will not fully work. I need to import time. If you don't have this, there is going to be something that is slightly weird here, is that you should not get any output. Oh, yes, I forgot, that's what happens if you copy paste from PDF, the quote mark is pretty weird. Okay, notice that there's no output. Okay, and the reason for this is because as soon as this function, so this one will return immediately. As soon as it returns immediately, it will exit the main function. After you exit the main function, the entire process closes. So anything that is left not running will be terminated. For us to force this to run, we can say that we want to wait a little bit for about, let's say, 5 seconds. This one doesn't really show you the step-by-step printing. This one just gives you the final output. Let's look at the Golang playground. The Golang playground, if you run this, you will see that this one will just be printed one by one. Okay. So let's try this again. You see that right? And that's because this one will go to sleep first, but after 250 milliseconds, it will go back and then print this. But the next one will also go back at around the same time, because the time is 250 milliseconds. Okay? So any questions on this? So what you have is basically something like this, right? You have the two Go prints. I color code them, so you have the blue and the red. When you use the keyword Go, it will return immediately, so that you can, once you call this Go prints, it will return immediately, and then you can execute this part. When you execute this part, you basically create the entire Go routine. Now this, the blue and the red can run concurrently. So if you do not if you specify a random time to sleep, yeah, you do not know which one will actually wake up first. Okay, this one we have a fixed time to wake up, so we have a very particular arrangement like this. But if you do not know which one will wake up first, then you can have a possible execution like this. You can have blue running twice, followed by red running once, and then blue run once again, and then red runs 3 times. This is just one possible execution, but any kind of interleaving may be possible. Okay, so that's a Go routine, because you do not know which one is going to be chosen to run.
The first time when the blue and the red is executed, just the first time when you execute the blue followed by the red, just for the first time.
It depends, because if you don't specify, if the sleep time is random, then you do not know which one will run first. But in this case, in this particular case, because I found that in this Go playground, it doesn't really, it only has a single thread to run. So it will have to order multiple Go routines to be linearizable. It cannot run both Go routines at the same time.
So because the main function is too big, so
this one, right?
Yeah. Does it go sequential, the first one and the second?
You create this Go routine first, and then you create this Go routine. Okay? In a multi-threaded processor, both can actually run at the same time. Okay, but the problem here is on the Go playground, they only have a single thread, because otherwise it's too expensive to give us multiple threads. Okay, so again, most of the time, this one will be printed first, because even though there's a slight time difference, right? And the slight time difference typically matters. What you should think about is basically you should not care about which one go first. Okay? The way you code this should be in such a way that it doesn't matter which one go first. The correctness of your code should not depend on which one go first. Okay? If you care about which one go first, then you need some way to synchronize the execution. Okay, so which I will show later. Okay, so for instance, you can create a communicating channel. The communication channel, as I said before, send is non-blocking, but receive is blocking. If you want to order certain operations, you can wait until you receive a message from the other Go routines. Okay, so this is how you can make a channel. The keyword, the function is called make. Chan here is a type. It's called channel, and it's a channel that can give type string. The data that you can push into this channel is only a string. This is the buffer size. Okay? If you give multiple send without the appropriate buffer size, the rest will be dropped. They either drop or it will actually be blocking. Alright? There is an operator that you can use to send and receive. So this is your channel. If you want to send, you should have the arrow on the right side, and then it must be pointing towards the channel. Okay? If you want to read, you want to receive, the arrow must be on the left side. Okay, and this is an assignment. So you read from the channel, and then you assign it to message. Okay, and again, this one is blocking. This one is not blocking. So you can actually have something like this. You can create the channel. Let's keep it as Boolean of size 1. Then you can say channel, I'm sending true. Right? And this is just to show that this is actually non-blocking. I can get flag channel. And then I can fmt.print line done. So ignore this, I can erase this. Erase time. Okay? So if this one is blocking, then I will not actually terminate. Because I'm sending to a channel, but nobody is there to receive yet. But here you will see that I think it's bool, like C. Yeah. Okay, yeah, this one is pretty particular. If you don't use a variable, it's just going to say it's failed. Okay? So this one is non-blocking. Because at this point nobody is trying to receive a message from here. Okay? But if you have 2, I believe it will block. Okay, because the second one does not have a space to go. Your buffer is only 1. Right? But until you send this, you cannot receive. Right? So at this point, the buffer is full. Because the buffer is full, the second send will have to wait. You cannot continue until the pipe is cleared. At this point, the pipe is cleared. But this one cannot run unless this one can finish execution. Okay, so there is this danger of having a deadlock. Deadlock means that everybody is sleeping, nobody can run. Okay? If you increase this to 2, then you don't have any problem. It's just that the second message is not going to be received. There is still one message in the pipe, and it's not going to be received by anyone. Alright? So any questions so far? Okay, what we can do with this is now we can order the execution. Because remember that receiving is blocking. You will not execute this until you have received something. So I can have a function that accepts the channel. The name is done. It's a channel of string. You can say print. And then sleep for 1 second. And then print this print line. Done. Okay, so now I can send the message here. So I already have the channel over here. All I have to do is call something with a Go routine. So this package is a Go routine, and I need to give the channel. And then I need to receive the message. And then I can print the message. Okay, so the order of execution is this. This one will create a separate Go routines that will know the channel. So the channel is shared between the two. And this one will send something to the channel, and this main Go routine will just wait until it receives something from the channel. So if you run this, I need to use time. Oh, it's Boolean. restrict this to 1 also. Okay? Then you do something and then it's done and then you get the message over here. Okay, so I don't need to sleep now, because this will force me to wait until there's something in the pipe, in the channel. Okay, so this will be the backbone for ordering which go routine should go first. Okay, so any questions on this first? Okay, so again the order is that this go routine will be created. You will try to run all of this. The main function here will block at this point. At line 18, it will stop execution over here, and then it will only continue execution until this something function has finished and returned a done via the channel. Okay, you can restrict the channel such that this one you cannot receive. This one can only send. If you try to receive something over here, then fmt.print. If you try to do this, it will say that it's going to give you an error, because you are not allowed to receive from here. You are restricting it such that you can only send something. Okay? So again, the arrow always go towards the left. So if you see that the arrow is going into the channel, then that means the channel is only for sending. If the arrow is going out from the channel, then that means the channel is only for receiving. Okay? If you don't have anything, then it can be used for both. Okay? So if I don't have this, I can run. Alright? We do have a certain kind of problem here. Because if you make multiple channels, we have two functions, F1 and F2. F1 will receive channel 1, F2 will receive channel 2. The question is, which one will be received first? Okay, because here, we say that this one is blocking. So the execution will stop over here until you receive something, and then you can continue on here, even though there might be already a message over here. Remember that F2 here sleeps for 2 seconds, but F1 sleeps for 3 seconds. So there is actually a message at the second channel before there is a message at channel 1. Okay, but because of this ordering, we are forced to wait for the F1 to give us something first before we can print this one. Okay. This can be a problem, especially if you don't care which one is sending. So let's have a demonstration. This one is F1. Three times. F1. F2 will just sleep for 2 seconds or 1 second. So F1, C1, F2, C2. So I can print immediately while I'm reading. Okay, so C1 will always be, the result from F1 will always be printed first. CH1. Okay, just wait for 3 seconds. Right? So notice that the F2 is printed immediately. because the message has been there waiting to be received. Okay. But if you reorder this, then you can print F2 first and then you wait for F1 to actually finish. Okay? Because this one is F2 can be printed after 1 second. F1 can only be printed after 3 seconds. But if you reorder this, F1 can only be printed after 3 seconds, but by that time, F2 can already be printed immediately. Okay, so to remedy this, there are a few ways. One is that you can always have one channel, and this one channel can be shared by the two. Okay, so this one now it doesn't matter which one. You give me first. But this has a slight little problem, is that if you do not give enough buffer, then one of them will wait until the channel have enough buffer size. Because you can only store a single message within this channel. Any other message will block until the single message is received by anyone. So you can always set it to 2, but again, if it's 2, then you are not sure whether both will be utilized at the same time. You may give too much buffer. So one of the possible way to remedy this is to have this thing called select. Select here, you have multiple cases where you can read from multiple channels. As soon as any one of these gives you something, you will go into that particular case. So if C1 finish first, then you can print this one. Okay? And only that one. And then you just exit the select. But this one is in a loop. So this is how you write a loop. Notice that you don't need the bracket. You run this twice. So the second one must be from the other channel. Okay, so you can, for I equals to 0, I less than 2, I plus plus. Select. Case, message 1. Okay, so now if you do this, it doesn't matter which one go first. You can receive both at the same time. Right? Because it's as if you have these two channel read occurs at the same time. You try to read from all of them. As soon as any one of them gives you something, you go to that particular case. So if I have this, one. You can see which one is actually going. Yeah, sorry, got too used to Python. Okay, so it goes into this case first. Because channel 2 is going into the go routine with the function f2, and this one is sleeping for a fewer number of seconds. Okay, so it's as if you are reading from multiple channels at the same time. And then as soon as one of them gives you something, you just go into that particular case.
So the for loop,
it just guarantees that you will read twice.
looks like a while loop.
This for loop?
Yeah, this for loop will execute and finish without waiting for anything.
It will block. It will block at the select.
Okay.
At this particular select, it will block until you receive something. Okay, so I can show you this. print I. Okay, so you will block here. As soon as you either you will block here at the select. As soon as you either receive channel 1 or channel 2, you can then continue with this, and then you can continue with this. Okay, so F2 0 and then F1 1. Okay, so it blocks right over here. Okay, good. Any other questions? Okay, so that's how you can read from the channel. So what about applications? Why do we need this? What are the things that you can improve by making things concurrent? Okay, so most of the time, if you have multiple core in your processor, then as soon as you parallelize it, it's going to improve. Okay? For instance, look at this Fibonacci. This is how we can parallelize the Fibonacci. And in fact, I can show you a scheme where if you have any recursive function, you can always parallelize it easily. Okay, so the way we're doing it is, so let me show you how it is. First, create a standard function, Fibonacci. And then let's call it n here, it's an integer. So this is the non-parallel version. If n, I don't think I did the bracket, but I haven't actually tried. Return 1. Okay, so here we can have an intermediate one. Okay, so pretty standard Fibonacci. The way we're going to do this is that first we need a communication channel. Okay, so we want to convert this into a parallel version. First, we need a communication channel with the exact type of our return type. Okay, so if our return type is an integer, we need to have a channel open for integer. Any return statement, or let's call it red. Okay, any return statement will be changed to sending message to the channel. Okay? Now the other thing is that because we add this return channel, we need to create our return channel. Let's call it red 0. We need to create this. To make channel of integer, let's say you just give it 1, or if you want to be very, very nice, just give it 2. Okay, just make sure that you will never block anyone. Okay, so now given this, all you have to do is change this into a go. Okay, and then you remove this assignment. The assignment itself is changed into reading from the channel. Right? Okay, now if you want to make it really, really pedantic, this one you just make it to be red 1 here, and then you have red 2 here. You can kind of have an ordering. You cannot receive F1 until you cannot receive F2 until you have received F1. Okay, so if you have then you need to have the second return channel. Now we can just make it work. Okay. Okay, so that's the standard method. Remember that, notice that the middle one here doesn't change. What changed is only slightly you need to give the channel. The channel is in place of any return function, a return statement. Whenever you want to call a recursion, you wrap that with a go routine, and then you create the channel first, and then you read from the channel. Right? So again, so we can always, this one will actually run nicely. We have read return channel is make channel integer of size 1. Then we can go call fib let's say 6 on this. Okay, the result will be from this return channel, we can print. I don't need this. Okay, this one will block until the execution finish. Right, I think I can go up to 16 easily. Okay, now change this to the old one. Where I have return instead. Now I need to remove all of this. Yeah, too many arguments. I don't understand this. It's return, right? Too many arguments to return. Oh, I think I have to specify this as an integer. I forgot how to. I didn't think I did this before. Function integer. Okay, wait. Golang return type. That one is name. Okay, the type is after. Okay, again, I think this is the main problem with the type inference, because if it's recursive, you cannot infer the type. It's still pretty fast. Let me show you 26, maybe it. Okay, it's actually very, very fast. Let's see if we can make a difference over here. Okay, this one took longer. Yeah, this one took longer. Weird. But typically it will be faster, because you have, if you have a multi-core processor, then the multiple Fibonacci can run at the same time. Okay. So yeah, so that's one of the advantage of having concurrency. Now, there is one very particular use case where you will definitely have a major advantage, and that is search. Okay, search here, you only need to find one instance of it. Okay, so if you can spawn multiple threads, and as soon as one of them gives you something, you can terminate completely. Right? So that's our aim. And to do that, we will need this function that accepts this one is here. Yeah, this one it returns nothing. I just want to terminate completely. Okay. The main thing here is that it accepts an array, but it only accepts a slice of an array. Okay, so you have this is one of the standard practice in Go is that if you declare an array, you need to know how big the array is. Okay, so similar to C. You can kind of slice the array. So if you do this, if you don't specify how big it is, you need to slice the array. And the way you slice the array is using this. Kind of similar to how Python slice things. So if you know Python, this means that on the other side. You want to slice this array from index 0 to this side. And then this one is from this size to the end. Okay, so here I'm just splitting it into two, but you can imagine that if I want more, I can always split it smaller. And I don't have a size, I don't even have an array. A variable array which is array at I is equals to I. Okay, so let's say this equals to I. For simplicity, my size is, can make this variable. Right, so this will be the index when I start it, and then whichever one finds it first. Whichever one of these finds it first, so yeah, I have to make the channel. Make the channel of size 1, then just give this channel. Now I don't care whichever one finished first. I can just print from there. Okay, so I can just run it. Right? So it's at index 42. Okay, so let's try to make this to be more complex. Give me a prime number, a large prime number. List of prime numbers. Let's look at the large. 199 is, let's say, times 7 mod 199. So this is prime, so I'm guaranteed to go over all the number, but I don't know where. Okay, so in fact it will be at this location. Okay, so notice something weird here is that this is where I slice, right? I slice it into two components. So I have an array initially of size 100,000. I slice it such that on this part is only 50,000. This one is 50,000. Right? One of the major things here is that if you look at this, the code remains exactly the same. My index starts from 0, it ends at this. So even though I slice it, each of these will be smaller. I don't care where it is. This one, the starting index is still 0. Okay. Also, if you don't slice it, if you don't slice this, what will happen is that it will. So if you don't slice this, it will be too big for this because you will need to give 100,000 over here. Then you can give the array. So if you try to do this, the error message is that the argument is too large. Because 100,000 array is, each of them is 4 bytes, so you have 400,000 bytes. This is a very large number, so you need to do the slicing. Okay, if I start from start until start plus size, okay, on one of them I will get out of range. Okay, even though technically I have 100,000, right? But because I slice it, this one, the index, starting index is 0. Okay, so slicing simplifies the multi-threadedness of this. Okay, so any questions?
I think the return is like 40. Okay.
Return is just basically I want to stop executing completely.
The buffer for this is the buffer 1 or 2?
Buffer is 1.
Okay.
So as soon as I get a result, I will just terminate. I don't care where it is located. I just want to find the first occurrences of this. Okay, so this, the more Go routines you have, the faster it will be. Because each of them has to search only for a smaller set of numbers, if they can run in parallel. For Fibonacci, everything is to complete. Okay, so you need to have everything finished. But here, as soon as one of them finishes, you don't care which one it is. You will basically just terminate. Okay, because you are only reading from one of them. The other one will, if the other one finds something else again, then it will just basically stop. It will block there.
Hold on, when you receive when you receive at this line, do you all the run onlys get terminated or they are still running?
If they find something, they will get blocked over here. Okay, they will get blocked over here. But after you finish receiving this, the main function terminates. Once the main function terminates, everything else will be terminated.
So after print, then it terminates.
Yes. Okay. So yeah, so basically anything involving search, if you just need one solution out of all the possible solutions, it will be much faster if you do it this way. Right. There are some interesting application of multi-threaded. There's this dining philosopher. So, or what I will call as a poor philosopher. So there are 5 philosophers here on the table. There are 5 food, but only exactly 5 cutleries. So if this one is trying to eat something, this 2 cannot eat, because this one is used. Okay, when you use both cutleries on your left and your right. So the question is, can you simulate this such that there is no if there's no deadlock, basically. You don't want any deadlock. There's a possibility of deadlock by doing this. If this one if everyone takes the left one, and then as they try to take the right one, they notice that the right one is not there. Okay? So what should you do then? If you force your way through, you wait until the right one is given to you, then nobody can eat. Okay? So that's the dining philosopher problem. Can you have a way such that there will be no deadlock? And actually the philosophy here is to just be nice. If you already take the left one and you try to take the right one and it's not there, you just return the left one and then try it again. It does not have a deadlock, but then it has another problem called a life lock, where you keep on taking the left one, and then when you see the right one is not there, so you keep on returning. And then when you try again, you try from the left one again. And everybody keep on doing that exactly at the same time. Okay, so that's a life lock problem. Everybody is doing something, but they're doing something useless. You just keep on taking the left one and returning the left one. Okay, so you can try to simulate this with a Go, because Go is kind of like the easiest way to simulate multi-threading. Right? And then there's the common one, which is the producer-consumer problem. You have a producer that is in an infinite loop, keep on producing something. It will wait once the buffer is full. The consumer will just consume things. It will wait once the buffer is empty. Okay, so this one is actually quite trivial in Go. I can have producer, and even I can say that this channel is for sending only because I'm a producer, right? And let's just give a number. And then I have a consumer. The channel is only for receive. There's a while true. I say that channel send I, and then I equals to I plus 1. Okay, here while true, I read from the channel and then I just print. Or just print it. And then let's just print a space. Okay, so now I can create a channel. Of integer, and then let's say my buffer size is 15. And then I can go producer, or let's go consumer first. Okay, just to make sure that the consumer waits. We'll just do this first, and then go producer. Let's just let it run for 5 seconds. Okay? Fine, we'll just use 4. You basically 4 infinitely long because you don't have any check. Why is not? Oh, yes, this is CH. God. This compiler is so strict. J is declared. So, yeah, the process took too long. Let's be nice a little bit. Let's sleep 4, 10 milliseconds. Also here. Okay, now this one makes more sense. Okay? So that's producer-consumer problem. It becomes trivial here because as soon as the channel is full, the buffer is full, then you will stop. Okay, so let's try to simulate that by having this one runs at a slower time. The consumer consumes it much slower. And let's reduce this. Okay, this one is too fast. Let's not sleep here. Yeah, but yeah, I mean, in the end, as soon as it goes to sleep, this one will go on releasing. But the main thing is that this channel will never be the channel will never overflow. Okay. It's basically as even if I don't sleep here, it will be as slow as this. Okay, so if I change this to 250, then you will see that it runs slower. Okay, because I keep on consuming. Now, let's have a print line here. To check whether we really get what we are getting. Okay, so this one is producing, this one is consuming. This one is print line. Line. Okay. So produce 5 first, and then this one consume, and then the 6 is actually produced afterwards. I should rearrange this such that this one is on top. This I produce first. Now you will see that then again, if I do this, the producing and the consuming will be, yeah, this one is consuming. Okay, but anyway, that basically blocks over there. I cannot really have a very nice printing here, because this one, as soon as it's consumed before it is actually printing, so as soon as I receive something, it clears the channel. So before I'm doing this one actually already runs again. Okay, so that's what is happening here. Okay, so any questions? So yeah, so notice that at any point in time, the size will be kept constant. Okay, so that's the power of the Go language with this very simple Go routines that makes multi-threaded programming very, very easy. This has a lot of applications, especially in server. So if you create a server, typically you want it to be multi-threaded. So once you receive a request, you create a Go routine to handle that particular one. Now it's very, very cheap to produce that particular thread. So in fact, there was an article back in 2012, I think, 12 or 13, that there are a few websites that says once they create the original server using Python. Once they make the capacity to be full and they want to expand again, they convert everything to Go. And the speed was improving by a lot because they can handle, the Go language can handle, with their server, they can handle up to 100,000 requests per second. Okay, that's not actually that big, but it cannot be handled by Python before. Okay? So Python is a very slow language. So yeah, so that's Go language. Any questions? So again, this one is not testable, so it's just something for you to play around if you want. So yeah, so there's a review. This is just very few slides. Basically what we have done so far. So this was the course objective. So we covered quite a lot of key concepts in programming language, and we covered a lot of functional programming. Until the very end, we covered concurrency. This is what we covered. There was actually, I think, this is an old version that they typically teach you Python, but I don't think there's enough time to solve that thing. So I just make it. Yeah, I just cross it. It was already crossed when I modify this slide. Okay, so you don't really miss much. Okay, so concurrency with Golang is not tested. The one that is tested is only until OCaml. There's a logic programming with Prolog as well as the CLP component of it. So yeah, CLP is constraint logic programming.
What about OOP with OCaml? Because there's
Yes.
no tutorial on it. I mean, next week, this week is the last week already.
Yeah, so it won't be.
So OCaml won't be tested.
OCaml will be tested, but not on the OOP part. I will not ask you to create a class. Okay? So actually, hold on. The thing is, Prof Chin set up half of it. I haven't seen what the question he set up. So just to be safe, it may come out. But I won't be the one setting. It might come out as a probably MCQ.
What's the structure like?
There was a lot of MCQ, and there are 3 written.
It's about how much?
I'm not
What's the
exactly sure.
weightage?
So what I'm doing is I have a set of questions. I send it to Prof Chin because he will be the one determining the final layout. But my suggestion for the written part was about 666.
6 marks.
18.
6 mark each.
So total.
So how much is the paper in total? 100.
Sorry?
Oh, then got 80 plus.
Make it all MCQ lah.
Won't be so little. I think it's
Still can Not
You don't
30. Your midterm already. How many? 39 MCQs.
make it all MCQ.
So if you base it on this,
Wow.
Good.
yes, this was taught by Prof Chin also. If you base it on this, then it will be 50 MCQ. Right?
50 MCQs, then 3 written.
Huh? So this is a.
It is written.
What's your marks?
I mean, this module is for full time. It's also for full time.
Where's the question one?
Oh, this is
Also doing
the
all this.
this is the counterpart for the.
Yeah. Okay.
Looks similar.
Yeah, it is similar.
Okay, yeah, it's probably about 25.
Wait, the module.
Are you?
The one
Oh,
this one
25.
is more of a
1, 2, 4.
CS 2104. So if you want to practice, you can go look for this. I have a feeling that it was more of this. I'll send you an email once I can
Thank you.
contact Prof Chin. Because if you look at this one has 3 written, and the MCQ is 25.
So 35 short, 35
The MCQ, but the problem is MCQ is typically not released by the department. So if you back to the result list here, oh, it doesn't say MCQ is not released. Apparently it's not.
Still very Haskell AD.
Hmm?
Still very Haskell AD.
I can assure you for the 3 one that I proposed,
not
it has no Haskell.
I just study Haskell and Flask.
For your how important is the syntax? How important is the syntax?
Typically, I won't really care much as long as it's minor syntax error.
Are you going to mark the paper?
Yes.
That's a good move.
So typically what I do, so even unless this is very, very critical, right? So remember Python. Python indentation matters. So when I used to teach CS10 and S, we use Python. When I mark, if the indentation is wrong, I have to penalize. Because the program changes meaning completely.
How do you know the indentation is wrong?
That's why I always tell the student, write the proper indentation.
!aiyo!
Yeah, maybe for him the indentation is just one
No,
mini.
But it's quite obvious, right? So you draw a straight line, like
Yeah.
this, and if the indentation is supposed to be here, let's say you have return, but he write it over here, and there was something else here again, then it's quite obvious that this one is wrong. If it's somewhere around here, if you shift it somewhere around here, I will just give him the benefit of the doubt. But if it's obviously here or even further, then it's definitely wrong. So that was my criteria for Python. Because for Python, indentation really, really matters. But for this one, if you do minor syntax error, like let's say for this you put equal instead of equal, doesn't really matter as long as I know what you meant. Okay, but the problem is that you read equal, but it's supposed to be not equal, like with a bang. That means I have to assume that you meant equality. If you forget to define the variable, again, it's not so much a problem here, but if you forget to define a variable, I would probably not really give much error.
So the format will be like 3 open-ended, 6 marks each, and then 25 MCQs.
At least that's what I propose.
Oh.
Prof Chin is kind of like a Haskell guy, so that means
Yeah,
yeah.
Haskell and OCaml. Haskell is not my favorite language.
So full time also learn all these languages. Yes, this one.
Except for Golang, because Golang, he told me to have one that is extra. So I just create one. It took me a while to create this because I use his template. This template is quite hard to work with. Okay, so yeah, so that's what we have. Then this was just the history. Go was actually the latest language that we covered. It was only created in 2009 by Google. It's not Go. Go is not a short of for Google. So Go is actually they want to have another Go with a programming language. Yeah, so they have a very weird structure, as you can see. Before the type is actually after and it's not separated by anything. So for instance, I think I have this. If you want to say what is return type is here. We claim that it gives a much better readability. In the sense that it's a function called producer that accepts this and returns an integer. Okay, so that's how you should read it. As opposed to other programming language.
Okay.
But as you know, Scala also have this, so I guess they take their inspiration from Scala.
Have you heard of Rust?
Huh?
Rust.
I've heard of it, not really a fan of it as well. It's quite close to Python, right?
I thought it's C++ actually.
Really?
Yeah, I think it's quite close to C++.
There's this one which is the worst language.
It's not around anymore, right?
It is actually.
Oh.
You can still you have some people who kind of try to torture themselves by learning Perl. You all know what is it called? Perl is the inspiration for Perl is regular language. It's a regular expression. Perl uses a lot of regular expression. So if you do not know regular expression, you're probably going to suffer in Perl. Yeah, so you basically have a lot of regular expressions there. And learning regular expression itself is already pretty terrible. Now you have an entire language dedicated on using that. Yeah, but I can tell you this is not even the worst language. There's some language that I cannot even mention. I can type it. It's, you only have this symbol, plus, minus, shift, shift, and this. Okay? So, and then they extend it to a few other things for output and input. So you basically go into some location, you either increase or decrease the value, and then you can go into a loop.
Similar like assembly language.
Huh?
Is it similar to assembly?
No, it's even worse than assembly.
Okay.
Assembly, at least you have add, you have subtract, you have
Yeah,
multiply.
small
This one
operators.
you have to go into cell by cell. You increase that. They have this is to add two values. This is an add function.
That's crazy.
This is the hello world.
Oh.
This is hello world?
Oh.
Where's the fish? Hello world.
It's just basically people have some kind of competition of which one can create the worst language. But then there was a, I used this before on a, not 2104, but on a compiler course. Because when you do a compiler, you want the language to be as simple as possible. And this one was the simplest language. So there was a bonus question that basically create an interpreter for this. Create a compiler for this. And there was one that is, you have a C program that you compile to VF. I'm not legally allowed to say the name. Okay, so yeah. Not the worst programming language, but not the best. These are what we call the standard programming language, not those that are designed to torture you. Lambda calculus is the oldest one, is before any kind of programming is done. It's in 1930s. Designed to actually capture the essence of mathematics, to capture what can actually be computed by mathematics. So you have a mathematical object that produces another mathematical object, and then you get a recursion. Okay. So the main takeaway is that this is basically what Prof. Chin likes. The types are very important. Okay, so he's very fond of the sum and product types. For normal users, typically what you want to check is basically that the type makes sense, at least internally on your mind. Even though there's a type inference, you should have at the back of your mind what should be the expected type over here. Okay? So you do not have to fully, if you know that there's a type error at the back of your mind, then you can understand whether or not the program may give an error. Okay, so if you can mentally figure out what will be the type, it may make the programming easier. Okay, immutability is basically the essence of functional programming. You don't change anything, you don't have any side effect, which can give certain kind of problems in Haskell where you cannot even print. Okay, that's the laziness, sorry. Immutability doesn't really give you much problem, but typically it's very impractical to write everything as immutable. If you want to speed things up, it's good to have a shared memory location so that you don't have to keep on copying things. Okay? Dynamic typing is a Python thing where a variable, I should have removed that. A variable A can be assigned to value, and then at the next line can be assigned to string. It does not have a very fixed type. I think what we learned is mainly static typing here. OCaml is static, but with polymorphism. But once you say that this is something, you cannot change it again. Like the ref type you cannot change to something else. Again, this is what the construct that we go through. Lambda calculus, I don't think we really cover that much. Monad we cover a lot, because in Haskell we need monad to print. Here there's an IO monad.
Answer the lot, but don't understand. I think my opinion is Prof. Shin a bit high up in the ivory tower when he talks to us. That's what I feel now.
Here,
Yeah.
in the Babel. Monad is monad can be thought of as a way you can okay, so look at the simplest part first. Okay, monad is a way you can describe what surrounds this particular object. It can be the environment. Then you can have the environment monad. Okay. If you know what surrounds it, the computation of a particular value may depend on what surrounds it. Think of it as let's say you look at, in the physical world, you look at particle. Right? If you look at the Newtonian view of it, it can move in a certain direction. If you know the speed, we know where it goes next. Right? But when you look at the quantum realm, it says that we cannot know either the position, we can only know one of the two precisely. We cannot know both the current position and the speed. We cannot know both with high precision. So what you can represent it is that it is kind of a monad, where the monad says you can only read one of them. Once you read one of them, the other one is erased. So there is an environment surrounding this particle, and the environment changes if you do an operation on it. Okay, that is why monad is typically the type of structure that is used to arrange a particular, to basically create a program that is composable. So if you create, if you got a function f with v, right, and then with some kind of sharing. Here, let's say v is let's say this is a list. Okay, you call a function f that is a list, so you can change the list. You can append something into it. Okay, so in the terms of monad here, this particular function is surrounded by a particular definition of what LST is. So you have the context for this particular function to run. Now you can have the two comparisons. If the function run within the same context, it must produce exactly the same thing. So you can do a functional analysis by using a monad, because you know what is the context surrounding the particular object. Okay, so that's basically what a monad is.
Is it possible to explain the quiz question 41?
This question. Which one is it?
The next one, is it? The next one.
Yeah. Oh, lab 4, below. There's the tutorials and labs problems. Yeah. Lab 4A. Yeah.
4A or 4?
Both. I think it's the same. Answers. The first one. The last question.
那个我操，那个 email 答案是谁发的？email 就是这堂课的 email。是他俩，我没看到，不知道是啊。不知道，他们都是人聊。 两个答案，两个分数。
Yeah, without the question, I don't really get what the answer is. This one, the monadic implementation.
Yeah.
I can tell you what the problem with this is. Because on this particular one, I think, it is an error. Oh.
Because you please also.
What?
On one of them, I think. On one of them, the who itself gives you an error. The type cannot converge. Where is who?
36.
I think 38. 38.
38.
Yeah. Who?
The type.
This is who, right?
Yes.
So who is a function that accepts two things, two functions. In fact, the first function must accept an integer, the second function must also accept an integer. And then you put them into H7. The result of this goes into H7. Okay, and this one,
Return the top of is a Y.
the do method actually returns you the original monad, I believe. Okay, anyway, this is something specific to Haskell, and I'm not really an expert in Haskell. I haven't touched Haskell for a long time, so can't really help much. But the problem, the specific problem with 41 is that at some point the implementation is wrong. You cannot get the type for that.
So.
And because you cannot get the type for that, then no implementation can give you anything that is correct.
So.
Because it is basically.
Oh shit! I'm so confused.
It depends on what the particular monad that you're using.
Okay.
Because you expect two monad, right? But if one of the monad is if it's a function monad, it will behave differently than if it's a list monad. So there is really no generic form of this. Because remember, for a monad to work, your execution must. For a monad to work, you need to be able to. Taking things out from the monad is easy, but you also need to specify how to create the new box. You need to specify how to create this, right? But if what you expect to be created here is different each time, then you need to have a very specialized function for each one of those. Which means that there's no generic function that can allow for this.
Oh.
Okay? Yes, any other questions?
Just to clarify, the return and the arrow, does it mean the same thing or?
Yes.
Return.
No. Error is this one, right?
Yeah.
So.
This one is a
Monad operator.
yeah, it's the other one. I forgot. It's byte. Is the one that takes out. I believe.
Oh, okay.